Hello, chemists! So, welcome to Chapter 10, where we will be talking about liquids and solids. So, this builds off our gases chapter in Chapter 9. Like previous chapters, Chapter 10 is not very math intensive. It's based more on conceptual concepts and putting all of our knowledge together into understanding how liquids and solids behave and some of their behaviors. There is just one or two calculations that we'll do, and I'll emphasize that and point that out when we get to there. All right, so this is our last chapter. All right, so in chapter 10 with liquids and solids, because molecules are closer together in these phases, we will be talking about intermolecular forces. So these are forces that occur between different discrete molecules. We'll look at properties of liquids based upon the intermolecular forces present. We'll look at phase transitions and diagrams, and then finally look at properties of solids. So let's get started. So why do intermolecular forces matter? So if we look at the different states of matter, gas, liquid, solids, and at a microscopic level, look at how those molecules, how close they are to one another in these three different samples, you see that in the gas phase, the particles are very far apart. And as you condense a gas into a liquid, you bring those molecules closer together. And then in a crystalline solid, those particles are even closer together in a very ordered array or pattern of molecules. So you can see how as we go from gas, liquid to solid, particles get closer together. In a molecule or in an atom, we know that protons and electrons, that those are held together through electrostatic interactions and sharing of electrons in molecules. So those are intramolecular um, uh, forces holding atoms, molecules together. Intra meaning in one molecule. Intermolecular forces, so kind of like the word international, so like between different countries. Intermolecular forces are forces that occur between different discrete molecules. So what are the attractive or repulsive forces between this molecule and this other molecule? So kind of thinking like a different country. International, intermolecular forces, so forces between molecules. So you can see, since in the liquid and solid phase, particles are closer together, so intermolecular forces are more important because molecules are closer together. All right, so how intermolecular forces show up in our observations and our observations of samples, whether it exists as a liquid or a solid or a gas at room temperature and pressure, is based upon intermolecular forces. So the physical state that you see a substance is at a particular temperature and pressure. So let's just say ambient temperature and pressure, like on Earth. What phase does, nitrogen, diatomic nitrogen, adopt? So we know nitrogen is a gas. So that observation that we make is dependent on two different things. It depends on the kinetic energy of your sample. That kinetic energy is dictated by whatever temperature that your sample is at. The temperature essentially is a measure of average kinetic energy of your sample. So that's how much energy that your sample has. So that's one of the factors that dictates the physical state of a sample. The second factor is the attractive forces between particles. So we know that diatomic nitrogen exists as a gas in ambient temperatures, but a different substance, such as like diatomic bromine (Br2), exists as a liquid in at room temperature and pressure. So how both of those molecules are diatomic? Why does one sample exist as a gas and another sample exist as a liquid in the same conditions? It's dependent on these two opposing forces: temperature, which gives it the kinetic energy of the sample, and then what we're going to learn here now is attractive forces between particles. So these are our intermolecular forces, particular or specific to that sample. So intermolecular forces are attractive forces. So these are the forces holding those molecules together. So, predicting the physical state of a sample is really a balancing act between, okay, how much kinetic energy does the sample have in terms of temperature, and then how much forces, attractive forces, are holding that sample together. So, you can see as you increase temperature, soon enough you'll break those attractive forces between molecules and then make it turn into a gas, right? And so it's this balancing act, and we'll kind of work through these concepts with temperature and intermolecular forces as we go on in this chapter. And so just note the magnitude or the importance of the kinetic energy versus intermolecular forces changes at different temperatures and pressures, and we'll see that in phase diagrams. So remember in chapter 9 when we talked about gases, gas particles are far apart from one another. And so when we were talking about kinetic molecular theory, we said that the forces between molecules are negligible, unless we're talking about real gases. So this is how we kind of segue into liquids and solids, because now the particles are close together. So now those attractive forces are important. So kind of thinking about it like a thought experiment, when pressure is high, meaning that in a gas sample, when pressure is high, when we're talking about real gases, those particles, those gas particles, are very close together. So attractive forces start to become important. Or when temperature is low, when those molecules are moving very slowly, there's not a lot of kinetic energy there for complete elastic collisions. So this is why attractive forces become important when gases are kind of close to becoming the liquid phase, either at high temperature or at low pressure. So examples are like liquid propane, the propane tank that you fill for your gas grill. You take that gas and you put propane gas into your cylinder, and you get a very high pressure in your gas cylinder. And so propane in your gas, in those grill gas cylinders, are in the liquid state because inside the cylinder there is a high pressure, and essentially intermolecular forces are keeping those propane molecules close together, so they're in the liquid phase instead of the gaseous phase, until you open up the tap and release the gas, and then now that gas is at regular ambient pressure, so a lower pressure, and then thus becoming the gas phase again. But it's stored, liquid propane or propane in your cylinders are stored as a liquid until you want to use it, and then becomes a gas. Or another example, liquid nitrogen. So liquid nitrogen, although I haven't shown any demos with liquid nitrogen in this course yet, but liquid nitrogen is a liquid, so you can condense nitrogen from the air into the liquid phase, but it's only a liquid. Nitrogen is only a liquid at a very, very low temperature. It's about negative 196 degrees Celsius. So it only exists as a liquid at a really, really low temperature. This is like 80-ish Kelvin. Like, that's really low. And so particles in the solid or gas phase are much closer than in the gas phase. So that's why intermolecular forces are important. We also refer to liquids and solids as condensed phases because we have taken those gaseous particles and brought them close together. So we say in that process, the verb for that is to condense gas particles into either a liquid or solid phase. All right, so now that we've talked about why intermolecular forces are important, let's talk about the different intermolecular forces that we can identify in a sample that I give you. Again, so molecules in a sample are held together in the condensed phase, either liquid or solid, through attractive forces of different molecules next to one another, bringing them together. And so those attractive forces are called intermolecular forces. The basis of intermolecular forces are electrostatic interactions. So attractive forces between positive charges and negative charges is the basis of intermolecular forces. So the strength of intermolecular forces, forces between molecules, is much weaker than an actual chemical bond that holds a molecule together. So yeah, intermolecular forces are weak in comparison to bonds, but the strength of intermolecular forces is still important enough where it can dictate some of the properties of chemical matter, chemical and physical more like just physical properties of matter, is where the strength of intermolecular forces can change some of those things. And so intermolecular forces are those forces are strong enough to control physical properties such as boiling points, melting points, vapor pressures, and viscosities. And so we'll see that it's a simple trend. As intermolecular forces go up in a sample, then there's a certain trend in regards to boiling point, melting point, vapor pressure, and viscosity. And we'll talk about the trends, after we've introduced all of the intermolecular forces. So here's an example of a sample of HCl. So we know that hydrogen and chlorine has a dipole moment. It is a polar molecule because there is a delta or a difference in electronegativities of chlorine and hydrogen. I don't know what the number is, but the number doesn't matter because I know that chlorine is much more electronegative than hydrogen. And so it's these partial charges in this polar HCl molecule is what gives rise to intermolecular forces. So since HCl is polar, if you bring another polar HCl molecule close by, you can see that there is this attractive interaction between the partially positive end of HCl and the partially negative end of HCl. So this interaction between different molecules, different HCl molecules, gives rise to intermolecular forces. So that's one type of intermolecular force that we'll talk about between polar molecules. So we'll consider three different types of intermolecular forces that we'll talk about, and a fourth one that you'll kind of expand upon in 1220. There's three different ones that we'll concern ourselves with, and they increase in order of strength and influence. So the strength of these intermolecular forces increases going down. So it increases going down. So this first intermolecular forces, London or dispersion forces, is the weakest. And then dipole-dipole interactions is stronger than London. And then finally hydrogen bonding, which is really just a special, so it's just a special kind of dipole-dipole, special dipole-dipole with certain criteria, but it makes for a very, very strong dipole-dipole interaction. And so that's hydrogen bonding. And then finally, ion-dipole interaction is really only important in solution chemistry, and that'll be talked about in 1220. So we'll just worry about molecules for now, and that will use these first three types of interaction or intermolecular forces. So let's go into the details of all three. Actually, before we go into all of the details, let me just give you like the big picture of all three of these intermolecular forces. So the first one, London dispersion forces, all matter has London dispersion forces. And it's based upon the molar mass of the sample. That's what gives rise to the different, to the magnitude of that particular intermolecular force. So whatever its weight is in grams per mole tells you how strong the London dispersion forces are in that sample. Dipole-dipole interactions, excuse me, only are applicable in polar molecules, samples that contain polar molecules. So polar meaning that there is a difference in electronegativity or an overall dipole moment. So we need to have, a partially positive end and a partially negative end on the molecule itself that makes up the sample. And then finally, hydrogen bonding, again, needs to have a polar molecule, but again, I said that there was special criteria with hydrogen bonding. You need either a OH group in the molecule, a NH group in the molecule, or HF. So it's essentially, I'm going to write it like this, FH. So hydrogen bonding. So see in this example, there's a hydrogen in all three of these cases. So essentially this is a special dipole-dipole interaction where you have a partially positive hydrogen atom bonded to a highly electronegative atom, such as oxygen, nitrogen, or fluorine. All right, so now let's look at all of the different intermolecular forces, the first one being London dispersion forces. So the weakest of all of the intermolecular forces that we'll talk about is London dispersion. So this weakest intermolecular force is most important in nonpolar molecules. Most important in non-polar samples or nonpolar molecules that make up a sample. right? So essentially, what's happening, how these intermolecular forces arise that we call London dispersion forces are through temporary dipoles that occur in a molecule. And so what that means is, we need to come up with an attractive force, but nonpolar molecules don't have permanent dipoles in them. But nonpolar molecules do have temporary dipoles. So what a temporary dipole is so we have electrons in their electron clouds around a nuclei, and so those electrons are moving in space. They're moving quite fast. So if we kind of think about an atom here, let's say it has 2 electrons, so I guess this is helium. So it has 2 electrons and they're moving around in space. And so if we just took a snapshot in time of those 2 electrons and where they are, if both of the electrons are just temporarily on one side of the molecule, then you produce a temporary dipole. So if both of the electrons, I guess in this picture you see how both of the electrons in this picture are on one side of the molecule. So we have a partially negative end of that atom and a partially positive end of that atom, because all of the electrons are kind of on one side of the atom, but just in like one snapshot of time. And so this is a temporary, how do I want to draw this? Like this. So this is a temporary dipole, and it's a consequence of those knowing that those electrons are moving in their electron clouds. And so now we have this temporary dipole in one atom, and so what that will do is influence another temporary dipole in a neighboring atom. So we have this partially positive end of atom A, so what that will do if atom B is very close by is attract some of those electrons, because electrons are negatively charged, and it will be attracted to the partially positive side of that atom, that those electrons are attracted toward the partial positive side. So this is essentially the view of a temporary dipole, that although all of these atoms are neutral and nonpolar in their behaviors, that because electrons are constantly moving, we can produce temporary dipoles in certain snapshots in time. And so by making two temporary dipoles, those neutral and nonpolar atoms, just for a split second, can be attracted to one another. So really, to summarize, London dispersion forces are attractive forces between temporary dipoles. Temporary dipoles are a consequence of electrons moving around and having partial positive and negative ends of the atom just in split seconds of time. So a temporary dipole can also be called an instantaneous dipole because it only exists for a split second. And so it can go away after some amount of time, that instantaneous dipole can go away. And then this slide kind of just describes what I talked about before. If we have a temporary dipole in one atom, right, and then we have a partial negative and partial positive end of the atom, then that can induce another dipole in a neighboring atom. And this is just due to the movement and random motion of electrons. And so there in this picture, we have this attraction because the electrons in a neighboring atom is now attracted towards the temporary dipole in another atom. And so it's all about the partial charges that arise from the random movements of electrons. And we've talked about partial charges and how we symbolize them. And so, samples don't only include 2 molecules. There's many, many, many molecules. So you can see how London dispersion forces are kind of the net attraction between all of the partial positive ends of those temporary dipoles and all of the negative ends of the temporary dipoles. And you kind of just sum them all up with all of the different molecules that are in a sample. So London dispersion forces apply to all matter, but I noted that it's particularly important in nonpolar samples. The reason I say that is because nonpolar samples cannot have dipole-dipole interactions or hydrogen bonding. And those two intermolecular forces are stronger than London dispersion forces. So nonpolar samples can only have London dispersion forces as their only intermolecular force. So that's why it's particularly important in nonpolar samples. So how do we kind of figure out this? Oh, I will point out also that London dispersion forces are present in all matter, whether it's polar or nonpolar. But with nonpolar, it's more. So London dispersion forces is more important. And I talked about the reasoning of why nonpolar is important, but It's important to note that polar molecules also have London dispersion, but typically polar molecules also have dipole-dipole interactions, which kind of uh, is more important. Dipole-dipole interactions, because they're stronger, are more important in polar molecules. So we don't really have to worry about or look at London dispersion forces in polar molecules, because there are other forces that are kind of overwhelming the forces from London dispersion. All right, so how do we figure out the magnitude or the strength of a London dispersion force? It all has to do with polarizability of a atom or molecule. So what polarizability is just ease in which an electron cloud can distort itself. So essentially, how much can you move electrons in their electron clouds? So polarizability can be affected by two different factors: shape of the molecule, essentially how much surface area is in the molecule, so how much room do electrons have to move around. So surface area is room for electrons to distort, essentially. And then finally, the other factor that polarizability is affected by is its size. So the second factor that polarizability is affected by is size of the atom. So size of your atom, one, can tell you how many electrons are present in an atom or molecule. And so if there's more electrons around, there are more electrons to distort itself. Or you can think about, larger atoms can distort themselves. If you think of soap bubbles, if you have a tiny bubble, it stays in this like one spherical bubble shape. But if you have a really, really big bubble, and you can think if there's more electrons there, then it can distort itself and wobble and take on non-spherical shapes. So essentially, if a molecule is more easily polarized, would it be easier or more difficult to induce a dipole? So if you think of, can you distort the electrons to make a temporary dipole, then you would think that London dispersion forces would be increased. So London dispersion forces increases if a molecule increases its polarizability. Polarizability. All right. And like we said, polarizability depends on size and shape. But let's see how size and shape affect polarizability and then thus affecting London dispersion forces. So how does size affect it? So typically the strength of London dispersion increases with increased molecular weight, typically, unless there are other forces that come into play, like for polar molecules or something. So let's just kind of summarize that. So London dispersion forces increases when molecular weight increases. So that's essentially size. When size increases, London dispersion forces increases. So generally, because atoms that are larger have larger electron clouds, there are more electrons to polarize. So therefore, you can induce temporary dipoles more easily. And so this graph kind of shows you an example of the increased boiling point of different noble gases. So here you think, so this is also a concept we need to think about. This graph shows increasing boiling points of different elements. So if we think of what boiling is, boiling a sample turns a sample into a liquid to a gas. So essentially, when we boil, we are breaking all intermolecular forces in our sample. And so the higher the boiling point, the more intermolecular forces that are present in your sample. So that's what I have here. At the boiling point temperature, you overcome or break all your intermolecular forces in order to separate your molecules from a liquid to a gas. So higher boiling point means more intermolecular forces present. So, and we'll talk about these trends later. So when intermolecular forces increases, the temperature in which you boil to boil a sample also increases. So if we see here some different molecules or atoms, let's first look at the noble gases. So neon, argon, krypton, and xenon. So you see here are their boiling point temperatures, and you see that they increase as you get to heavier elements. I mean, xenon is much heavier than neon. It has more protons, neutrons, and electrons in xenon than neon. So here you clearly see that as as molecular weight increases, intermolecular forces increases in the sample, and what you see is the temperature at which you boil increases. And so you can see the same thing for our diatomic halogens as well. So we have diatomic fluorine, chlorine, bromine, and iodine also. So again, we're just kind of going down the periodic table, and so you can see the heaviest of all of the halogens has the highest boiling point. And so a consequence of these different boiling points that you see in the diatomic halogens, so diatomic fluorine and chlorine at room temperature, which is about, let's just say it's about 300 degrees. So let's say this is room temperature, about. So at room temperature, fluorine and chlorine are gases, right? So if we had a sample of fluorine or chlorine, we'd have to have it like in an ampule or something, or some type of closed container, because those substances are gases. But see how bromine, its boiling point is slightly above room temperature? So bromine actually exists as a liquid at room temperature. So that's for diatomic bromine. So if we had a sample of bromine, it's typically a liquid. It's one of one of two liquids that exists at room temperature and pressure on the periodic table in their elemental or their natural state. Finally, iodine here, which you see has a much higher boiling point than all of the other halogens, is actually a solid at room temperature. That's for iodine. So this is showcasing exactly how I was saying the physical state of samples is dictated by the intermolecular forces present in that sample. So because iodine has the most intermolecular forces present in that sample, there's a lot of forces keeping that molecule together, or keeping that sample together. So at room temperature, at that specific kinetic energy, that there's not enough energy to overcome the intermolecular forces, so iodine exists as a solid. Okay, so how does shape affect London dispersion? Excuse me. London dispersion forces. Essentially, how does shape affect polarizability? So what we were saying is that as surface area increases, polarizability increases, therefore London dispersion forces increases. So let me just write that there. So as surface area of a molecule, surface area increases, polarizability of a molecule increases, meaning it's easier to distort those electron clouds. Therefore, intermolecular forces increases. So what you see here are two different isomers of the same molecule. So this is pentane. So there's 5 carbons here. So in these two examples, we have a 5 carbon chain in a straight line versus this is called neopentane. So we have like 1 carbon in the middle and then 4 carbons around it, while in this example we have 5 carbons in a straight chain. So in this example, in our straight chain, there is more surface area around the whole molecule itself, because you're kind of elongating it, you're taking advantage of all of the surface area, making it as large as possible. So this has more surface area. So what that means, linear molecules have a larger surface area, so there's more space. Electrons have more space to distort themselves. And so what you'll see is that pentane here has more London dispersion forces, more intermolecular forces present in its sample. Oh, I'll write, instead of intermolecular force, I'll say London dispersion forces increases here. And actually up here I will write as, no, that works out. Intermolecular forces increase, boiling point temperature increases. Okay. All right, so here, yes, so linear molecules have more surface area, so therefore have more London dispersion forces present in that sample. Versus spherical molecules, you're kind of smushing all of those carbon atoms close together, so there's less surface area, and what that does is reduces the amount of intermolecular forces present. And so you can see how those intermolecular forces, London dispersion forces, manifests itself in its boiling point temperatures. So the linear version of pentane has a higher boiling point than the spherical version or of neopentane. So since the boiling temperature is higher, then that means that this sample has more intermolecular forces present, because its boiling point temperature is greater than that of our neopentane. All right, so that summarizes London dispersion forces. Again, important in nonpolar molecules. Pentane, in this example, is nonpolar because bonds between carbon and hydrogen fall in our covalent type of bonds. So these are nonpolar molecules. So let's look at the next type of intermolecular force, and that is dipole-dipole interactions. So I'll just remind you that London dispersion forces are the weakest of all of our intermolecular forces. Then it's dipole-dipole. So dipole-dipole are stronger than London dispersion forces. London dispersion forces are based upon temporary dipoles, right? That's what we talked about, temporary dipoles. So dipole-dipole interactions are based upon permanent dipoles. That's what you see here on this slide. So molecules that have permanent dipoles, they don't have to make temporary dipoles. They're attracted to one another because you can think of them as like little magnets. And so what you'll see is that any molecule with permanent dipoles tend to have higher boiling points than nonpolar molecules that don't have permanent dipoles. And it's because of electrostatics. Again, but now these electrostatics. But now these partially positive and partially negative ends of the molecule, they're permanent there. They're permanent in space, that they don't only exist for a split second of time, they exist all the time. So that's why dipole-dipole interactions are stronger than London dispersion forces. So typically if a molecule if you're comparing two molecules, one being polar, one being nonpolar, the polar dipole-dipole interactions will be the more dominating force holding that molecule together. However, if a molecule is much, much heavier, then London dispersion forces will also dominate. So this kind of explains some of our anomalous boiling point temperatures that we see. If a molecule is so heavy, then London dispersion forces does dominate. So you can see here in this picture showcasing dipole-dipole interactions, it's very similar to our London dispersion diagram of showing how molecules are attracted to one another. The only difference here is that these molecules have permanent dipoles. Think of them as magnets, just kind of being attracted to one another, which is very, very important when you have samples in the liquid and solid phase, because molecules and atoms, or I guess not atoms, but molecules are much closer together. All right, so here is just a table showing the different properties of samples with dipole-dipole interactions that we will compare. So if we look at these nonpolar cases for diatomic fluorine and argon, right? So at these nonpolar molecules, only London dispersion forces are present. And so you can see that both of these different, this molecule and argon atom, they have very similar molar masses. So what you see is that they have similar boiling points. So similar molar masses, so similar boiling point temperatures. So that's kind of cool how that works out. But so that's our nonpolar set. Let's look at polar molecules. So we have polar molecules, which will have London dispersion forces and dipole-dipole interactions because they are polar. And what do we see here? HCl and H2S, they are polar. I tried to choose substances that have similar molar masses to our nonpolar cases, but their boiling points are much higher than our other two nonpolar interactions. So these ones, our boiling point temperatures are much higher than nonpolar substances here. And that's because our dipole-dipole interactions are dominating with these polar molecules. So essentially these two examples have way more total intermolecular forces present than our nonpolar samples. So here's another example kind of showcasing the power and the strength of intermolecular forces when it comes to polar molecules. We have two different molecules, acetone and butane. So N-butane, so meaning that it's in a straight chain. And so both of them have are in similar sizes. They have similar molar masses, but our acetone sample here has a much higher boiling point, about 56 degrees Celsius, while butane has a boiling point of almost 0 degrees Celsius. And so, again, that is a consequence of intermolecular forces, that this molecule, our acetone, has much more intermolecular forces present, so it will have a higher boiling point. It has a higher, acetone has more intermolecular forces because it can have London dispersion forces and dipole-dipole because it is a polar molecule, while And butane is nonpolar. It's a nonpolar molecule, so it only has London dispersion forces. So the total amount of intermolecular forces is much greater in acetone.